right, so today we're going to be starting series. The other thing you should know is that we are not using the same textbook for the next 2 units. It's the Larson textbook. It's also on Google Classroom. The one thing that's different about it, if I remember correctly, is that each section is a separate PDF as opposed to the whole chapter as a PDF. Okay, so it's the Larson textbook. I quite like the Larson textbook for series. I don't like yours nearly as much. Um, I used to use the Larson textbook for all of calculus, but there's parts of it that I don't like. He very much likes to do, like, do you know all the trig identities? You have to do this in order to be able to do this integral. And I'm like, no, no. Let's do calculus. Let's not do a review of obscure trig things. So anyway, today we're going to start series. You might be wondering why we're starting in section 9.2 instead of 9.1. 9.1 of Larson is sequences, which we have done already. Okay, so infinite series, hopefully you looked at these at least a little bit in pre-cal. So if we have an infinite sequence a sub n, then the summation as n goes from 1 to infinity of a sub n, which is the sum of all of the terms of that sequence, is called an infinite series. So an infinite series is just the sum of the terms of an infinite sequence. So the numbers a sub 1, a sub 2, etc. are called the terms of the series. They were also called the terms of the sequence. It's the same. Now, one of the ways we can find the sum of an infinite series in some cases is to consider the following sequence of partial sums of the series. So S1 is just the sum of the first term. It's just the first term. S sub 2 is the sum of the first two terms. S sub 3 is the sum of the first three terms, etc., etc., etc. Through S sub n is the sum of the first n terms. If we can figure out how to write an equation for the sum of the first n terms, and then look at what happens as n goes to infinity, then we can use that sometimes to find the sum of the infinite series. So if this sequence of partial sums converge, the series is said to converge and has a sum equal to the same value. If the sequence diverges, the series is going to diverge. So if the sequence of partial sums diverges, the series is going to diverge. All right, so let's use a sequence of partial sums. Hello. Okay. There's someone in here. Okay. I'll do it. Thank you. It's from your mom. Yay! That's nice. Okay. So if we look at the sequence of partial sums, S sub 1 would be 1/2. The sum of the first two terms is 1/2 plus 1/4, which is 3/4. The sum of the first three terms would be 3/4 plus 1/8, and that turns out to be 7/8. And then the next one would be plus 1/16, which would be 15/16. So what we'd like to know is, well, what is the sum of the first n terms? Now, notice the denominator is always 2 to a power. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So the denominator is going to be 2 to the nth power. The numerator, notice, is always exactly 1 less than that. So that's going to be 2 to the nth minus 1. So the limit as n goes to the infinity of 2 to the nth minus 1 over 2 to the nth is 1. Therefore, the series, notice this is a sequence, the series converges to 1. Because the sequence of partial sums converges to 1. Now, also we could look at the original series that we added. What did these terms do as n goes to infinity? So the 1/2, the 1/4, the 1/8, the 1/16, the 1/30. Multiplying the denominator by 2. And what's going to happen as we get bigger and bigger and bigger? What kind of numbers are you going to get?
Big numbers.
In the denominator, so the number will be, it'll be really close to 0. Okay? So the terms of the original sequence go to 0. The sequence of partial sums converges to 1, so the series converges to 1. It's important to keep those three things straight in your head. It's really easy to kind of get them all mixed up. You can do kind of a cool diagram on this. Do a rectangle, and we'll make the border green. So if you do this, what's really going on here is you've got 1/2. I'm like, okay. Plus 1/4. That's 1/4. Plus, that's 1/8. Plus 1/16. Plus 1/32. Plus 1/64. You get the idea. I'm never going to actually color in all of it, but I'm going to be so close to 1 as makes no difference. Right, eventually you're not going to be able to tell that I have any part that's not shaded left. Let's take a look at this one. So my sequence of partial sums, this says I'm going to have the summation as n goes from 1 to infinity of 1/3. That means I'm going to add 1/3, and then add 1/3, and then add 1/3. So S sub 1 is going to be 1/3. S sub 2, I'll add another third, that'll be 2/3. S sub 3, I'll add another third, that'll be 3/3. S sub 4 is going to be 4/3. So S sub n, well, the denominator is always 3, and the numerator is always n. If I take the limit as n goes to infinity of n over 3, well, that's infinite. Therefore, this series diverges because the sequence of partial sums diverges. Also notice if you were looking at the terms of the series, it's 1/3, 1/3, 1/3, 1/3, 1/3. Do those do like the last one where they went to 0? No. Okay, that's going to become an important idea for us in a little while. All right, let's take a look at this one. This is a kind of an interesting case. So here, S sub 1 is going to be 1 over 1 minus 1 over 2 is equal to 1/2. S sub 2 would be the 1/2 that we already had plus the next term, which would be 1 over 2 minus 1 over 3. Let's see, that's 1 minus a third is 2/3. The third term in the sequence of partial sums is going to be 2/3 plus 1/3 minus 1/4, which is going to be 3/4. We notice on this in every case that the numerator is whatever term we're on, and the denominator is always whatever term we're on plus 1. So S sub n is going to be n over n plus 1. So if I take the limit of that as n goes to infinity, that's equal to 1. Therefore, this series converges to 1. The interesting thing is, if we were to just write out the first several terms, it would look like this. You would have 1 minus a half, right? That was this first part. And then you would have plus a half minus a third. And then you'd have plus a third minus a fourth. The next one would be plus a fourth minus a fifth. Notice what happens is that's 0, this is 0, this is 0. And what is this getting close to as we increase our term number? 0. So we end up with just 1. This is called a telescoping series. It's kind of a special case, because what happens is that all the stuff in the middle drops out, and you're only left with the very first term, and wherever you are, the last term, which is getting closer and closer to 0 as your term increases. The reason it's called telescoping is if you think about, like, you watch a pirate movie or something, or some sort of sailing movie, and they have the handheld telescope that you open up and it expands and then it contracts like that. When you say something is telescoping, it's not it can see a long way. It means it folds up into a compact shape. Okay, there's actually a thing that can happen to you if you either you get dropped from a sufficient height or something heavy gets dropped on you. Your spine can actually telescope. Right, there's squishy bits in between the vertebrae. Now, if it's heavy enough, well, they don't come back, and that's bad. That's now you're talking likely paralysis and the whole deal, because the nerves get squished between the two bones. Anyway, on that happy note, we'll look at a specific series that we're going to come back to multiple times. Did you guys do geometric series last year or the year before?
Yes.
Okay. All right, so the series given by, the summation is n goes from 0 to infinity of a times r to the nth, which is equal to a plus a times r plus a times r squared, blah, 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 etc., etc. For a not equal to 0, a can be any constant, but it can't be 0, is a geometric series with ratio r. This series diverges if the absolute value of r is greater than or equal to 1. Now let's think about that for just a second. If r is greater than or equal to 1, our terms are going to be getting bigger, right? Now, it may be that they're getting bigger, and they're alternating signs, positive, negative, or whatever, but the terms are getting bigger all the time. Whereas if R has an absolute value less than 1, then the terms are getting smaller. If R is equal to 1, all of these would be A, and that would be just like example B up here. You're just adding that same number over and over, and again, that's not going to converge. Now, if the absolute value of R is less than 1, the series converges, and this is one of the few that we can just look at and go, I know what that's going to converge to. Most series, we're going to be content with it converges or it diverges. We're not going to be super concerned with what does it converge to. And what it converges to is A over 1 minus R. Does that sound at all familiar to you?
I think so.
Okay. So let's take a look at these. Determine the convergence or divergence of each series and find the sum if convergent. So this is a geometric series. You may want to rewrite it as 3 times 1/2 to the nth power. So the absolute value of R is 1/2, which is less than 1. Therefore, the series converges. And we know what it converges to. It converges to A over 1 minus R. So A is the value of the first term. You do have to be careful. Every now and then they'll be sneaky and change this from 0 to 3 or 1 or something like that. So you have to go, okay, when I substitute in this initial n value, what is the value of this going to be? That's A. So A is just 3 over 1 minus R. So 1 minus 1/2. That series converges to 6. All right, let's take a look at this one. This is also a geometric series. In this case, the absolute value of R is 3/2. That's what you're multiplying by each time. Since that's greater than or equal to 1, this series diverges. Because the terms just keep getting bigger, and you're adding on those terms. It's never going to stop at some particular value. All right, last page. Notice that if we have a convergent series, then the terms of the series must be equal to 0. Right? If the terms, the limit of the terms has got to be equal to 0. Your terms have to get really small. Be really careful of this idea. This is called the nth term test for divergence. It says then that if the limit as n goes to infinity of a sub n is not 0, then this series diverges. Your individual terms have to get close to 0 as n goes to infinity, or your series is never going to converge. However, you can't use this to prove convergence. Just because the terms get small doesn't mean that your series is going to converge to something. It may not. Basically, the way I think about it after a long time of thinking of it, it's the terms of the series have to move towards 0 quickly. If they take their time, then the series may not ever converge. So let's take a look at a couple of these. determine the convergence or divergence of each series. If it's not a geometric series at this point, the first thing I always do is check the nth term test. So I just go, okay, what's the limit as n goes to infinity of n squared over 5n plus 12? Well, that's infinite, and that's not 0. Therefore, the series diverges by, and I like to quote the name of the series, by the nth term test for divergence. If you just say the nth term test, it's sufficient. I like to add the for divergence to remind me it cannot be used to prove that anything converges. All right, let's take a look at this one. As n goes to infinity, n factorial over 2n factorial plus 1. Now, both the numerator and the denominator are going to go to infinity. That's pretty apparent. And it's not something that we can use L'Hopital's rule on because, well, how do you take the derivative of a factorial? I don't have any idea. I don't know that you can. It's beyond what I know. But how much does this plus 1 matter as n goes to infinity? Yeah, not at all. So really, this is going to act like n factorial over 2n factorial. The n factorials will happily cancel each other out. This is equal to a half. That is also not equal to 0. So the series diverges by the nth term test for divergence. Let's take a look at this one. If we take the limit as n goes to infinity of 1 over n, that's equal to 0. You're like, great, this one converges. Well, we don't know. At this point, what do we know? More work is needed. We could try and do the sequence of partial sums. The first sum would be 1. The second sum would be 1 plus a half. So that would be 3 halves. The next sum would be 3 halves plus a third, which is, if I add a third to that, that's 9, 10, 11 sixths. The fourth would be plus 1/4. So that would be 44, 45, 24ths. I don't see a nice pattern there. At this point, we don't know enough to be able to tell whether this converges or diverges. Spoiler alert, it diverges, but just barely. It is sort of, in my mind, I think of the summation as n goes from 1 to infinity of 1 over n as the dividing line between things that converge and the things that diverge. It's right there on the border between the two. We'll find out why probably Monday or Tuesday. I mean, Tuesday or Wednesday. All right. And that's it.